Okay, so let's talk about three-phase generator. From my previous video, I talked about three-phase systems, polyphase systems. Now, essentially, on polyphase systems, what you have is a system with three lines. So when you have a single phase system, you have this load, this source, and then you have a line that delivers power from the source to the load, and then you have a return path. Now for three phase systems, what you have is wait lang. This one, you have a source, and then you have a load, and then in some cases you have three lines for phase A, B, and C. In some cases, you have four lines where the fourth line is your ground or your neutral. Now, I'll be talking about three-phase generators. So, the idea of three-phase generator is that you basically have three separate coils that act, each coil acting as a single-phase generator. So, in this case, this is an example here. I have a set of coils for phase A. It's one generator, basically. It's one single phase generator. I have another single phase generator for phase B and another one for phase C. Well, I guess what's important here is that they are built in one machine. They are built in a single machine such that the separation between the coils will produce a difference of 120 electrical degrees between the different phases. Okay, so since you have three sets of coils, so if this is your source, right here, you have three lines that represents the terminals of each phase. One for phase A, one for phase B, one for phase C. Now, so how does it look within this box? How does it look within this box right here? So if you have a three-phase generator, those three sets of windings, this is winding 1, winding 2, winding 3, can have two types of connection. The first one is your Wye Connected Generator, in which case your three sets of coils are connected to a common node, which we call neutral. So that common node is the common of the three coils, and then the other terminal of the coils will go to the lines. You have line A, line B, and line C. This is actually the connection here, represented here. As you can see, the other end of the coil goes to the lines A, B, and C, and then the other end of the coil, the other one, goes to the neutral. They are basically connected with each other, such that you have a common node for those three. So that's Wye Connected, or star connected. Sometimes it's called star connected. Now, the other connection that is possible for those three is your delta connected generator. The idea here is that if these are your three sets of independent coils, you connect those three. Well, they are not in parallel with each other, but you connect the two terminals of each coil with each other. So you connect the two terminals of this coil to these coils, and then the two terminals of them to this one and this one, such that you have something that looks like delta or a triangle, or sometimes it's called mesh connected. Okay, so what's the difference of having this type of generators as compared to your single phase generators? On your single phase generators, if this is your generator, this is a single phase generator. If this is your generator, single phase generator, you have two lines basically. One line to deliver power, and then the other as a return path, such that the voltage is defined as the voltage between these two lines. Now, sometimes this line is grounded, sometimes this is grounded, so the voltage is between your line to ground, but still it's between two nodes. Okay, so and then you have a current here that is basically the same as the current here, going back to the source. Now for three-phase generators, the main difference is that instead of just considering these lines, you also have a voltage between the line and the neutral. So it's not just the voltage between the line and the line. So you have a voltage between the line and the neutral. By the way, if you're wondering, you can treat it as if one of these lines or two of these lines are delivering power, and then one of these lines or two of these lines serves as your return path. Or you can treat it as all of these three lines deliver power, and at the load they sum to 0. So that's one way to look at it. Okay. Sometimes you have a fourth line from the neutral connecting the neutral of the common node to the neutral of the load. So sometimes that happens. So instead of having 3 lines, you have 4 lines. Okay, but anyways, what I'm trying to say is that instead of just having your voltage from this point to this point, if you have a 3-phase generator, you actually have 2 types of voltages. One is the voltage between lines, that's called line to line voltage. The other one is the voltage between the line and the neutral, and that is called line to neutral or phase voltage. So the difference there is that, well, your voltage, line to line voltage, is measured from the line to another line. That means it's from line A to line B to line C to line A. So you have 3 line to line voltages. For line to neutral, you actually have 3 also. Your line A to neutral, line B to neutral, and then line C to neutral. So, well, what you have is 6 different voltages as compared to single phase generator where you only have 1. The voltage of the generator. So in this case, you have 3 line to line voltages, and then 3 phase voltages. Now, for the current, what you have is for the current, what you have is a line current that is in the line, and then a phase current. Now, for Wye connected generators, since your phase, this phase current is in series with this line current, therefore we can say that the line current is equal to the phase current. However, for generators, for Wye connected generators, the voltages, the line to line voltages and the line to neutral voltages are not equal. So how to do this, I think, yeah, okay. So it is always that it's always correct to say that the line to line voltages is greater than the neutral voltages. So vectorically speaking, the line to line voltages in terms of magnitude is greater than the phase voltage by square root of 3. So that means the magnitude of the phase if the magnitude of the phase voltage is 1, then the magnitude of the line to line voltage is square root of 3. If the magnitude of the phase voltage is V phase, the magnitude of the line to line voltage is square root of 3 V phase. It's always greater than. Now, as you can still remember, we have the phase sequence from the previous discussion. So if your circuit is in ABC, your V line to line leads V phase by 30 degrees. If it is in ACB, your V line to line lags V phase by 30 degrees. So what does it mean? It means that if my VAB is angle 0, therefore if the system is in ABC, its corresponding V phase, which is VA neutral, is negative 30, because if AB is 0, therefore it leads by 30, so AN must be negative 30. One way to look at it is that if this is AB, voltage in AB, it is leading voltage in AN by 30 degrees. So that is if it is in ABC. If it is in ACB, therefore the voltage in AB line to line lags the voltage in the neutral by 30 degrees. So what does it mean? If AB is in 0, therefore AN is in positive 30 degrees because it is lagging. Nahuhuli siya. Okay? So the same goes for lines BC and then line CA. So the correspondence is that if it's voltage in AB, the correspondence is in AN. If it's in BC, the correspondence is in BN. It's CA, then the correspondence is in CN. So yeah, it goes the same way for either ABC or ACB sequence. Okay, now what if your generator is connected in delta? If it isn't connected in delta, well, you still have the line-to-line voltage and the phase voltage, the line current and the phase current. However, if you look at the voltages, this is the phase voltage and then this is the phase current. This is the phase voltage, sorry, and then this is the line-to-line voltage, and they are in parallel. Therefore, as compared to Y, if it isn't connected in delta, therefore the line-to-line voltage is just the same as the phase voltage. Now, if you look at the line currents, then you cannot say that they are in series because of the triangle here. So the line current at A is actually a KCL of this current and this current. Sir, how do I know the direction of these phase currents? These are your phase currents, this one here. How do you know the direction? Take note that this is a generator and your positive current always goes out of the positive terminal of the voltage. So that is a source. Yeah. So that's the direction of the voltages. Of the currents. Sorry. Now sorry. Saglit lang, i-mute ko lang to. Yan. Okay. So these are your currents here. If you perform KCL, you get this line current here. If you perform KCL on this current, you get this line currents here. If you perform KCL on these two, then you get this current line. Yeah, I see. Okay. So how does it differ from your Wye Connected Generator? If we are in ABC sequence, wait lang. If it is in ABC sequence, this one, your IA your line current IA, lags the current at AB by 30 degrees. So it's actually easy to remember. In ABC sequence, take note, in ABC sequence, if it's Y, your line-to-line leads phase. If it's delta, your line lags phase. And the correspondence is AB, BC, AB to AN, BC to BN, and then CA to CN. Okay? And then if it's in ACB, if it's in Y, your line-to-line lags your phase. If it's in delta, your line leads the phase. All of them by 30 degrees. Okay? Yeah. So that actually works. I guess let's just use that for now. But there are times where you cannot use that that lagging and leading by 30 degrees when we are in unbalanced systems, but we'll deal with that later. I guess sa ngayon, for now, let's just use that mnemonic, yung ating the relationship between the line to line parameters and the line parameters and the phase parameters. Okay, so that is your Y and delta generators for 3-phase systems.